In this lecture, we're going to continue on with inferences for one population parameter. Last week, we looked at inferences for one mean. And in this lecture, this week, week 5, we're going to take a look at inferences for one population proportion. Now, the word proportion here means percentage. So that's what that is. And here I have listed a few examples of percentages for us. For instance, the percentage of US adults who have health insurance, percentage of technology stocks that make up the S&P 500, the percentage of cars in the US that are imports, exports, whatever, and the percentage of US women in the labor force. So you can see you can make up your own percentages, but the idea is that we have a proportion or a percentage that is actually unknown in the population, and we would like to infer to it from the sample. So how are we going to do this? So first of all, let's define what a population proportion is. A population proportion, namely P, is equal to X over N. Here X is the number of subjects or items or objects having the attribute that we're looking for. And capital N, the denominator, is the population size. So it's just a simple ratio of two numbers. That's all that is. Now our inferences come in the form of point estimation, confidence interval, and hypothesis testing. So those are the three things we're going to do. So first of all, a point estimate means a single guess. What is a single guess for estimating the population percentage P? Well, we're going to use it from the sample. We're going to use the same information from the sample. We're going to call that P hat. Okay, and let me see if I can enlarge this. Yeah, I can. So you can see a little better here. And there you go. So that's what P hat is. P hat is exactly that X over N that's directly above it. That's over here. Except P hat is from the sample. That's the key difference between them. Okay. And it turns out that this P hat is an unbiased estimator of population proportion or percentage P. So what does that mean? That a couple of things it could mean. One, if you look at the sampling distribution, that is the probability distribution of P hat, the center of that distribution is going to be exactly the parameter we're looking for, P. Now these are all theoretical work that we are referring to. Number one is. And so is number two. In number two, what we're saying is that the expected value, or think of it as the average of P hats in repeated sampling, yields the population percentage P. But remember, in reality, we only take one sample. We don't take repeated samples. And now, in order to do confidence interval and hypothesis tests, we need to know the sampling distribution of P hat. The sampling distribution of P hat turns out to be binomial. Now, for simplicity, actually, we're going to use the normal approximation to this distribution. And this normal approximation is due to de Moivre and Laplace. And this was discovered in the early 1800s. So there are a bunch of assumptions that go with this normal approximation to the sampling distribution. So here I have them in the paragraph. So if you assume that random variable X has a binomial distribution with parameters N and P, and the sampling is done with a replacement from a finite population, or that it's done without replacement from an infinite population. So that's the assumption about the X. Also, the assumption here is that our sample is large, and these two expressions that I have here, product of NP and N times 1 minus P. In other words, the NP gives you the number of successes, that's X, and N times 1 minus P gives you the number of failures. That would be N minus X. Both of those must be at least 5. And when that's at least 5, then the sampling distribution of p hat is only approximately normal with the mean and deviation that are given below. And there you go. So now let me go through this and explain what this expression means. This is p hat. That's the percentage from the sample. So the sampling distribution p hat, the tilde here means follows. It follows. N means normal. These are the parameters of the normal distribution, right? Every normal distribution has a mean and a deviation. So that's what these are. So this would be mu of p hat, and that's sigma p hat. So what does the mean of the distribution is? Look at that. That's p. That's exactly what's up here. Expected value of p hat is p. Mu is the mean, the center of that probability distribution. And the standard deviation of it, sigma p hat, is given by p, 1 minus p over n, square root of. That's pretty easy. Now, of course, we do this in Minitab, so you don't have to do this by hand, but it's just kind of nice to know a little bit about the theory behind it. Now, there are several ways we can construct confidence intervals and do hypothesis tests about the proportions. And we're going to take a look at the most common one that's in most literatures, most textbooks, and that's commonly known as Wald's confidence interval. This one right in here, Wald's confidence interval, which is named after Abraham Wald, who actually worked on this confidence interval. And there you have the formula. So the 1 minus alpha 100% confidence interval for p is given by p hat plus or minus a z alpha over 2 times the square root of p hat 1 minus p hat over n. Now the quantity that's to the right of plus minus all of this, this is what we call the margin of error. Okay, that's what that is. So there's the formula for confidence interval. What if we want to test the hypothesis test? Well, the hypothesis test for proportion. So the null hypothesis we're going to assume is p equals to a hypothesized value, which we call p naught. The subscript here on p. The subscript here on p looks like an O or a 0. This is read as p naught. And I have the correct spelling here. P naught. And this is what we call the hypothesized value of the proportion of the percentages. Now your alternative could be in any one of the three forms, right? It could be less than, not equal to, or greater than. And if you do this by hand, this is our test statistic, which is the formula we use to test this hypothesis. It's going to be a z. And again, z under the null, the assumption the null is true. That's what z sub 0 is, z naught. And it's given by p hat minus p naught divided by this denominator. Now, there's one thing you may have noticed here, interesting. Let me actually scroll back up here. So if you look at, let me see if I can use my pen here and do some drawings for you. Okay, so if you look at this formula here, okay, this one. So this is the formula for standard deviation of that normal distribution, the sampling distribution of p hat. Now, if you look in here, you actually see something that's slightly different than that, right? The difference is the presence of the hat or the caret sign on p. What's up here, actually, this is a theoretical distribution. But since we don't have p, we use an estimate of p, which is p hat, in that excuse me, in that theoretical distribution. Okay, so that's one thing I want to mention. The other one is actually now, if you look at this denominator, there's another formula in here, down here in the denominator. Again, try to compare this with what's up here for the confidence interval and with what's directly above it. So it looks like we got three different formulas. So again, to recap, the top one is the standard deviation of the sampling distribution. The one we use for confidence interval is driven from the sample, p hats. Okay. And the reason the one for the hypothesis test is different is because we always assume the null hypothesis is true. Well, if the null hypothesis is true, then this hypothesized value actually defines the center of the sampling distribution because we take it to be true, so we're going to use that in our formulation. And that is why we have 3 different versions of this. Okay. So now let me remove all the extraneous markings here that we don't need to keep things kind of clean, and move on. Okay, and our decision here, I'm going to go off of a p-value. Okay, and the software of course gives us p-values, so our decision is to reject the null if p-value is less than or equal to alpha, which is the size of the test or the significance level of our hypothesis test. Now, here I have an example from another textbook for you. I'm going to take a look at this one. I've done this by hand, so we're going to see the computation by hand, and then of course we go to Minitab and take a look how simple it is to run this exercise in Minitab. We want to need 2 things. We want to do a confidence interval and we want to do a hypothesis test. Okay, now this exercise actually doesn't ask you to do a confidence interval, but we'll make up a confidence interval ourselves for this exercise. So you probably read the statement of this exercise. This has to do with substance abuse and mental health. Okay. Sorry about this. This thing just pops up. Okay. So in this exercise, we have, according to this publication that's cited above, 13.6% of 18 to 25-year-olds were current users of marijuana or hashish in year 2000. A recent poll of 1,283 randomly selected 18 to 25-year-olds revealed that 205 currently use marijuana or hashish. So notice in here, by the way, the poll reflects the sample size here. That 1,283 is the sample size. Now, in this context, if these 18 to 25-year-olds actually are users of this substance, then that would be considered as a success, and that would be x, little x, the number of subjects having the attribute. The attribute here is using the substance. 205. At 10% significance level, remember this is your size of the test, which is alpha. Do the data provide sufficient evidence to conclude that the percentage of 18 to 25-year-olds who currently use marijuana or hashish has changed from the 2000 percentage of 13.6? So if you look at the last sentence here, we simply are interested to know whether the percentage, so right up here, percentage has changed. So this is the formation of the alternative. The alternative, the research want to know if that has changed. So the status quo is going to say what? It's going to say, nah, it hasn't changed. It's the same as the year 2000, and that percentage being 13.6%. Okay, so with that, we're going to actually now do this. Let's scroll this. Hold on, something isn't working here. Hold on just a second. Okay, so my note was somehow stuck. Okay, sorry about that, but let's continue on. So here's what I've done. I've actually written the hypothesized proportion right in here. That's P naught, 13.6. The sample size was given to be 1,283, and the success is 205, alpha 10%. All of this came from the exercise. The null hypothesis here reads P, the percentage is 13.6, which is the hypothesis of no change from year 2000, the base year. The alternative says the percentage is different. That means it has changed. Remember this last line, has it changed? That's what the alternative, the research want to know. And I've gone through the hand calculation. So I found the critical value. Remember on week 4 lecture, we talked about the 2 approaches to hypothesis test, critical value and p-value approach. So I'm showing you the critical value here. The size of a test, alpha, was 10%. The alternative is two-tailed, so we divide alpha by 2. And the z-test is what we're doing. A z of 05 is 1.645. I can get that from Minitab. And with that, I can actually identify these 2 rejection regions. You see that? Now, because alpha is 10%, a confidence interval that's 90%. See, its complement of 10% would be 90%. And this is a two-tailed test. So we can actually test this hypothesis using a 90% confidence interval also. But anyhow, here are our critical values. The critical values are 1.645, negative 1.645. And again, we have 2 rejection regions in the tail. And our test statistic, the formula that actually determines how far the sample percentage is away from the hypothesized percentage and scaled in the units of standard deviation. That's what the denominator is, a standard deviation. So p hat, that's the percentage from the sample. How did I get that 1598? It's right in here, right up here. Remember, 205 were users of those substances out of a sample of 1283. That gives me about 16% from the sample. So if you look at the difference between the sample and the hypothesized percentage, that difference is about 2.5% right here. See the numerator? So it looks like it's increased. It has increased according to the sample by over 2% since 2000. And then we divide that by units of standard deviation. And this tells us on a z distribution, that's the standard normal distribution, how many z-scores, how many standard deviations we are above 0. We are almost 2.5 standard deviation above 0. So that's kind of unusual value to have. And because it's sort of unusual, because it's too far from 0, then our decision, of course, is consistent with what we think that z-score of 2.5 would imply. And formally speaking, because 2.48 is bigger than 1.645, that means 2.48 actually falls into the rejection region, right? It's going to be right up here. You see up here the z, the right tail, is going to be in that tail, in that rejection region in the red zone. So we're going to reject the null. Remember, the null said there's no change in the percentage since year 2000. So our conclusion is that yes, that percentage has changed. So there I have the conclusion. The percentage has changed since year 2000. Okay. And I have it. Seems like it's gone up by about 2.3 percentages. Now, by the way, when you do these percentages, again, chances are you're not going to do this by hand. But if you did, make sure that you carry enough decimals. If you choose to do this by hand, we usually go to the nearest 10,000s on each percentages here. So please make sure you do that. Now, I want to find the p-value for this. And this is something, again, that I have for you if you're interested. Remember, Minitab actually gives you p-value, so you don't even need to know this. But theoretically, how do I find p-value for a two-tailed z-test? And this is how you do it. This is a formula for it. The hypothesized z-score was 2.48. So probability of z greater than that, I found that number from Minitab to be 0.066. Twice that because it's two-tailed test, and our p-value is 0.132. Minitab will confirm this for us shortly. And using p-value approach, remember, if p-value is less than or equal to alpha, we reject the null. In this case, 0.13 means 1.3% is less than 10%, so we do reject the null. And one thing that p-value tells us, it gives us the actual probability of a type 1 error. That's what it does. So that actual probability of type 1 error, that is rejecting the null when in fact it's true. That's 0.132. Again, to put that in context, that's what this means. There is 132 in 10,000. That's what 0.0132 means. That's 132 10,000ths. So 132 in 10,000 chance the null is true, and we made the wrong decision when we rejected it. You see that? That's the very definition of a type 1 error. And we feel like, well, if 132 out of 10,000 we made a mistake, the other side of that coin is 9,870 or 68 chances that we made out of 10,000 that we made the right choice in rejecting the null. And this is what the sampling distribution is. P hat, the center of distribution according to the hypothesized value of the percentage, P naught is 0.136. Units of a standard deviation, which is the denominator of our test statistic, was 0.0096. And we have observed a sample percentage of 0.1598. You see that? So we are actually in that rejection region, right in here. Well, you don't see the rejection region because I don't have it marked here, but this is what p-value is, 0.13. Actually, that 0.13, that's not right. Let me erase this one. That's not 0.13. 0.13 was the entire p-value, right? What we have is half of that. That's 0.0066. So that's what that was. 0.0066. Let me write that. 0.0066. Right. Because the other part of that is in the tail here. That's the other side of that. 0.0066. Right? That makes up the whole p-value. Okay. And this is the run from Minitab. So you're going to see some of these. I didn't do the formula for confidence interval by hand. We don't need to do that. I just want to show you how the hypothesis test is done by hand. So let's focus on the hypothesis here. So this is a test. The null hypothesis, P is 0.136 against the alternative it's not equal to. This is our test statistic, 2.49, p-value 0.13. And what did we find? Our p-value was 0.132. So we are a little more accurate. Minitab rounded it to the nearest thousandths. Now look at our confidence interval. Our confidence interval, 90%, runs from anywhere between 14 to almost 18% users now, let's say this year, of those substances in that age category, 18 to 25-year-old. The true percentage could lie somewhere between 14 to 18%. Okay, and the sample percentage shows about 16%. Okay, now here, event, that's actually the number of successes, X. So that's what Minitab calls it. Minitab calls that event. So that's actually your X value. Okay. And the method is normal approximation method is used for this analysis. Minitab actually does exact hypothesis tests, and it does also normal approximation, which what we want to do here in this course. Okay, and there we have it. And note, by the way, I can test this hypothesis using the confidence interval because it's two-tailed. And remember how this works. If that number 0.136 is inside the confidence interval, we do not reject the null. So 0.136 is just under 0.14, right? It's outside on the lower limit. So in this case, we reject the null hypothesis. What if I want to test, let's say, the null hypothesis that the percentage is, well, the percentage in year 2000 was 13.6. But if I wanted, let's say, if they told us it was 15%, we can test that hypothesis that this year is no different than 15%. So the idea being a whole range of hypothesized value for the percentage could be tested using confidence interval. So we're done with this one. Let me actually go and show you how this is done now in Minitab. So in order to do this in Minitab, we need to get some of these numbers, carry them with us. So remember, the event is number of successes. That was 205, and we did 90%. Our alpha was 10%, right? Okay, so let's go to Minitab and see how this is gonna work. So here I have Minitab open. Okay, and let me actually see if I can maybe enlarge this to where you can see a bigger portion of the area that I have. Recording area. There you go. And actually what I need to do is I do need to carry this all the way up, maybe, so you can actually see what I'm doing here. Okay, and there you go. We're good. So you actually are now seeing this whole Minitab thing. Okay, now let's go to stat, and we're gonna go to basic statistics. We've been there, right? Remember week 4 we went there and we actually did a z test, and we're gonna go down to proportion, right? Percentage. One proportion is what we're doing. Click, and then in here it's giving us an option. Do you have summarized data, or do you have one more samples each in a column? We don't actually have 1283 entries in a column here, so I'm going to use summarized data. And the number of event, again, it's already populated because I just ran this to insert it in my note. But for you it would be blank, right? It would be something like this. There you go. So this is what yours is going to look like, right? So number of events, again, you just type in 205. Number of trials, that would be your sample, 1283. And if you check hypothesis test, yours is default unchecked, check it. Hypothesized percentage, make sure you put it as a decimal, not a percent. It was 0.134, right? 0.134. And your options, here in the confidence interval, I'm going to do it 90. And here's your selection for the alternative, which is not equal to. And your options for the method, see, it does exact test and normal approximation. Make sure you check the normal approximation and hit OK, and you're good to go. And there you have it. So this is how you run this procedure in Minitab. Well, actually, let me see. I don't think I put in the right number. The 0.136, sorry, 0.136. So let me go back. Stat, basic stats, 0.136. I put 0.134. There, now it looks right. And keep everything else the same. Now we got exactly what I had before. So here's again the sample, the confidence interval, and this is our test statistic, and this is our p-value. So really all you need out of this work are two pieces of information. You need the p-value, which you have, and if you need the confidence interval, it's right there. Okay, and that should do it for us. So let me go back to my OneNote, and I think we were good to go on this one. Let me resize everything here to where it used to be, and that's all there is in this lecture. So we are pretty much done with one parameter inferences for, we did it for the mean, we did it for proportions or percentages, and that wraps this up. Now something about the margin of error. Let me go back here in our confidence interval that we just did, right in here. If you want to actually find our margin of error here, we could. Let me show you how you can do it from the from the confidence interval. Okay, if I want to figure out what the margin of error is for this exercise, I can actually find the length of the confidence interval. L is going to be 0.177. I'm rounding this number, the upper limit, minus 0.143. Okay, and if you subtract that, we're going to get 0.34, right? If I did it right, 0.34. Now, the whole idea, this is the length of the confidence interval. This would be E, and E, okay, the whole thing is L. So the length is twice the margin of error. So that means to find the error, you divide length by 2. So that means if I want to know margin of error, I can do the length, which is 0.34 divided by 2, and that will actually give me the margin of error for this exercise. And my margin of error is 0.034 divided by 2, or 0.017. 0.017. So that means, what does that mean? That means we are 90% sure that the maximum error in estimating P. See, right now we're saying P hat is from the sample 0.1598, right? That's this number right here. Well, this number could be in error. Okay, the maximum error of that estimate is 0.17 as a percent, 1.7%. So we are off by no more than 1.7%. So the estimate of the percentage this year of those substance users is about 16%, with a maximum error of about 2%, 1.7 to be more exact. Okay, so just want to point that out with regards to margin of error. Okay, so hopefully you followed everything we've done. If not, please go back and review the lecture, and hopefully it will make more sense the second time around. Okay, so with that, we are done with this lecture.